Okay, we're get started. Good afternoon, everybody. We're talking about spring still. Let's see, this is our first. No, we talked on Monday, so we can refresh ourselves a little bit on the springs, and let's go back and think about the conclusions from last class. We looked at. We spent most of the lecture discussing the wave functions, the solutions for these so-called harmonic oscillators. And remember, the guess that we made a couple classes before spring break was that the wave function of this system looks like a bell curve. The bell curve function, e to the minus x squared, what we call the Gaussian function, has the properties that the Hamiltonian for the harmonic oscillator needs. And so I showed you that it satisfies the Hamiltonian, the Schrodinger equation, that it in fact returns an energy. It satisfies things. But what we did see is that it wasn't orthogonal, right? That meaning that, remember, one of the principles of quantum mechanics is that whatever system we have, that it can be represented by a set of wave functions that are all orthogonal to each other, right? Those are perpendicular vectors. And so these are the functional forms of those vectors. And what we saw is that the bell curve, the Gaussian function itself, is not orthogonal. It doesn't form an orthogonal set of functions. Every product of a bell curve is a bell curve. So we had to introduce a orthogonalizing function, multiply our guess by a new function, just this h function here, the Hermite polynomial. And what we saw is that it introduces a polynomial. Could be an x or an x squared, x cubed, just depends on the energy level. And that gives us some oscillatory behavior within the potential. So within the turning points of the spring, this thing oscillates like a wave. And then outside of the potential, it looks like a bell curve. It decays exponentially. So we showed that we had to have that orthogonalizing function, and that gave us all the properties we needed. It satisfies the Schrodinger equation. It's normalizable, and it's orthogonal. So we have all the properties of waves that we would expect. And I showed you some picture. We wrote down some equations for this. Again, they're just equations. We'll do some calculations with them in the coming week. And there'll be some calculations on the homework, but it's just, they're just equations of x. And so we can calculate things with them. But the important thing is that it is what they look like. I think visually it's more interesting to think about them. And this is what we found. The wave function is quantized. The vibrations of the spring are quantized with a quantum number v. That could be any integer 0 or greater. And each of the wave functions corresponds to, say, a half period, a whole period of a wave, and 3 half periods of a wave, just like in the particle in the box. So we have the same kind of construction that we did in the particle in the box. We wanted to find waves whose wavelength, its periods, fit within the box. Right? We wanted to create that resonance condition where if the wave was bouncing between the edges of the box, that it constructively interferes with itself. And so that requires that any allowed wave of the system, any energy that's corresponding to a wave, to have to hit that matching criteria. And so that limits the energies that are allowed, the allowable energies and the allowable states of the spring, the oscillator. And these are the first 3 states that I've drawn here on the left, the wave function, and then the probability distribution on the right. We'll do some exploration of these soon, but I want to talk about the consequences of these today. We'll do a little bit of application probably on Monday. I want to talk about consequences. The 2 big consequences of this is, well, we can talk about the interpretation of the wave functions in a second, but the more interesting results about the harmonic oscillator are the energies of the harmonic oscillator, which are amazingly simple. Right? The energy of a harmonic oscillator is h bar omega, where omega is that spring constant frequency that we calculated for the classical spring. It's a function of the force constant and the mass. H bar omega omega has units of frequency per second. H bar is joule seconds. So H bar omega is an energy. And so that energy H bar omega is quantized with a V plus 1/2, right? So we just put in a V, 0, 1, 2, 3, 4. And so the energy levels are spaced in such a way. And that gives us energy levels at H bar omega over 2, 3 over 2, 5 halves, 7 halves. The reason why they're harmonic, why we call them harmonic, is because the spacings between the energy levels are fixed. Everyone is spaced by an octave. We have a fundamental note for our string, H bar omega, and every allowed note of that string is one of the octaves of that fundamental. So we have a fundamental note of frequency H bar omega over 2. And then every single one of the notes above that are spread by a single octave. Right? Hence harmonics. Just a classic music kind of harmony. This is different than a particle in the box. In the particle in the box, remember the energy has n squared in it. So the spacings between the energy levels in the particle in the box are not equal. In fact, the spacings get larger as you go to larger and larger n. Spacings get wider and wider. Here, no matter how many quanta of energy I put into my spring, the next level is always H bar omega away. If I want to remove energy, I just go down H bar omega. The consequence of this calculation, and we'll see the results of this and some consequences as we move through the class. We saw a similar thing in the particle in the box, but here it's really showing its ugly head. Is that the ground state of this vibration is not zero energy. So this is a motion that inherently always has energy in it. So no matter what whatever you do, imagine you have a machine that can extract all of the heat out of a material. Right? That's at least what the Thermo Fisher says it does. You can put a material in here, you can cool it down to arbitrary temperature, even 0. And what you would actually realize is that Thermo Fisher was lying about that claim, because you cannot cool things down to 0 Kelvin. And the reason why is that if your sample is a gas or a liquid or a solid of diatomic molecules, ABs, just like we have here, if you pull all the energy out of those molecules, then all will be in a ground state. The lowest possible energy level for the vibration of that molecule is V equals 0. That's the lowest possible state it can be in. And no matter what I say is that I always have, even in that lowest energy, some residual energy there, some residual heat, H bar omega over 2. So no matter what I do, I can't remove that energy. Always there. And this is a fundamental consequence of quantum mechanics, that there is this so-called 0-point energy. And this is the reason why 0 Kelvin is an impossible thing to reach, is because you will always come across a system that has 0-point energy eventually, and you can never remove that energy from the system. It's a consequence of quantum mechanics. Now, I'm sure that Angie's sitting up here wanting to ask, how can that be possible? I know that's probably a question you may wonder. Why? How can you always have energy? Why can't you remove it? And so that's an issue. And I'm going to pretend like that.
I thought it was absolute 0. Like,
right, so
that was. Sorry.
Right. Remember that absolute 0, it means that is equal to an average energy. Remember, the average energy of a system at thermal equilibrium is roughly RT. So the average energy of a system at T equals 0 is 0 thermodynamically. But the average energy of a bowl of harmonic oscillators at 0 Kelvin is H bar over 2. Can't be any lower than that. So what that means is that 0 Kelvin is a contradiction. What that means is that 0 Kelvin is not actually reachable. It's impossible to reach. The most energy that you can, the least amount of energy you can have in a molecule is H bar over 2. Or H bar omega over 2. We'll look at the consequences as we move through. This is going to be something that appears rears its ugly head every once in a while. It's not really ugly. It's actually a really beautiful result. There's a lot of really interesting consequences for this zero. You guys may remember, for those who took classes in the last semester, okay. We had this conversation near the beginning of the semester about intermolecular interactions. And I talked about the van der Waals effect. And the way I described the van der Waals effect was to show you this experiment where we took two metal plates and brought them close together. And we saw that those metal plates attracted each other. The Casimir. The Casimir effect is a consequence, it turns out, once you do the math and work it out, there's a consequence of this 0-point energy. The electrons that are bound to each metal plate, you can kind of think of them as being an oscillator. They're stuck, they're like little springs attached to the atoms. You know, these electrons on the metal that are bouncing back and forth and vibrating. They always have some residual vibrational energy in them, some oscillatory energy. And so you have, no matter what temperature you're at, you have these two plates with electrons that are just wiggling and oscillating all the time because they have the 0-point energy. And because those two wiggling together causes them to interact with each other and then therefore generating an interaction. So 0-point energies are tied into all sorts of behaviors that we observe in chemistry. But I hopefully will show you some more examples. It's a little hard to put your head around this idea, but it does have some powerful consequences. All right, let me show you a really cool another cool consequence of this theory. Remember that in the particle in the box, when we hit the walls, probability goes to 0. There's no possibility to find our particle that's been stored in that box outside this box. But in this box, this harmonic box, we don't have that luxury anymore. We look at the equation for the wave function of our system, we have an e to the minus x squared over 2. That value is non-zero for every x less than infinity. It may be diminishingly small. But what I know is that the wave function of the harmonic oscillator has a tail, an infinitely long tail that just decays off to infinity. What that means is that when we square that to get psi squared, the probability distribution, which tells us the distribution of bonds that we observe in a bond, the distribution of lengths that we observe, that means there's some probability that there are lengths outside the turning points. In fact, that the spring, if you think about it kind of like a classical spring, instead of it bouncing back and forth between the limits, so like we showed with the, excuse me, the classical spring, the quantum mechanical spring has some probability distribution outside the potential. So there's some probability that we would actually find the bond longer or shorter than you would expect classically. It can sneak out of the potential. The potential is slightly leaky. And I want to look at a consequence of that behavior. This leakiness out of the potential. So let's do just a little bit of math. I want to think about how bad does a quantum mechanical spring violate the principle that a spring needs to stay within its turning points at a given energy. So let's set up the problem. So we've got some stretch position, and we're just going to set it the middle to be 0. Right? This is some distance. We're scale it to 0. We have a potential, a quadratic potential. This is our potential energy surface. Right, 1/2 kx squared. Right, and imagine that I put some energy into this system. Let's say we're at v equals 0. Right, so I have an energy level here at v equals 0, which has energy h bar omega over 2. Okay. And we could say that there are two classical turning points, right? There's these points where the energy intersects, the energy horizontal line intersects the potential. We'll call that X minus and X plus. Right? These are the turning points. If this were a classical spring, I would know the spring would oscillate between these 2 points. So let's go ahead and impose on this our wave function squared. Let's think about the probability of our spring and where position it's at along this trajectory. And remember, the wave function for v equals 0 is proportional to e to the minus x squared. So that means that the square of the wave function is proportional to e to the minus 2x squared. So the psi squared is also a Gaussian function. And so it kind of looks like this. Something like this. This is psi squared. And so this, again, this function here, psi squared, tells us what the probability is that we find a bond at any of the lengths between x minus and x plus. So you think of 0 as being the equilibrium point. So this is like a normal spring at like rest. And so there are some bond lengths that are longer than that, some bond lengths that are shorter than that. And it samples all of them with bell curve. So we can kind of truncate this equation, this wave function, into 2 parts. There's this region inside the turning points, the classical region. And then there's this region on the outside, right, where the wave function begins to decay, but is beyond the turning points, right? So we can call this green shaded region the classically allowed lengths. And this other region is equal to the classically forbidden lengths. These are lengths that a spring at that energy would never show. A slinky would never be that long or that short. Right? What do I know about the sum of these two? Remember, I want to integrate. So the probability. What we want to do is we want to calculate the probability that the bond length. We'll actually do it like this. Well, first we'll think of the region in the center. Those are bond lengths between x minus and x plus, right? So that's the green region. Right? And then there's the region that's in blue. So then we can add to that the probability of x less than x minus or x greater than x plus. The sum of these must be equal to 1, right? Because that satisfies every point. This total probability has to be equal to 1 because it's normalized, and it's the sum of 2 components. I can break this down and simplify this a bit more by remembering that this function is even. Right? So the left side and the right side are the same. So I could write this as the probability of x minus x plus 2 times the probability of x greater than x plus. And this has to be equal. Okay, because the probability that x is less than x minus is exactly the same as it is x plus. They're symmetric. So I can just dump. All right, so how do I calculate these? Well, remember what I'm interested in is really what's the probability I find it on the outside. If I can know this number or this number, I know the other one. So let's go ahead and calculate that. All right, so the probability that x is greater than x plus is equal to the integral from x plus to infinity of the wave function times the wave function dx. Right? Remember, to calculate the total probability, we just integrate over the space that we are interested in. So I'm just integrating that blue region on the right. All right? So I can go ahead and plug things in. To plug in the wave function from before, we have that, but we don't really know what x plus is. X plus is going to be a function of the energy of the system. Because the more energy the system is, the wider the potential, and therefore the wider the turning points are. So the turning points have some behavior that's a function of the wave function and its energy. So we need to figure that out. So let me just write this on the side. It's a pretty easy calculation to do. All right, well, we know that the total energy of this system is 1/2 h bar omega. Right, that's what we defined. And this energy intersects the potential at that point, at x plus. So I know that this is going to be equal to the potential at that point, which is 1/2 k x plus squared. So that means, therefore, I can just do some calculations that x plus or minus is equal to plus or minus the square root of h bar omega over alpha squared k, where alpha squared, I'll write it down in a second. And we have that the wave function for this system in the ground state is equal to, write it down, alpha over pi to the 1/4 e to the minus alpha x squared over 2. Okay, so x plus or minus is this complicated equation of a bunch of things. All right, but I know that h bar omega, right? I can simplify some of these things because there's a k in omega, and alpha also has some k and mu in it as well. Let me remind you that alpha is equal to the square root of k times the reduced mass divided by h bar. Right, and once you plug all of this in, you find that x plus or minus is equal to plus or minus 1 for v equals 0. That's really nice. All right, so let me remind you really quickly. So what I just showed is that the turning points for this system are at plus or minus 1. Right? That's the easiest solution that I could come up with. And that's a really convenient answer. So all I need to do now is integrate this function from 1 to infinity. And then we have psi squared. So that's going to be the square root of alpha over pi times e to the minus 2 alpha x squared over 2 dx. And this is equal to, I'm not gonna work out the math.
Wait, if it's negative 2 alpha x squared over 2, then wouldn't that make it negative alpha x squared? The 2's would cancel each other out.
Sure. Yes, I agree with that completely. Yes, I agree with that. Yeah, that's fine. Right, and this turns out to be a function that you can solve numerically with just a calculator. And it's equal to 0.0785. Okay, so what does that say? It says that there's the probability of being in this forbidden region is 7.85%. That's the chance that you're going, when you measure the bond, that you're going to find it at some length slightly larger than you would expect classically. So the total probability of finding outside in the blue region is twice that number. So this number right here is 15.7%. It's exactly, almost exactly 16%. What that says to me is that a bond, when you observe it, if your molecule, you can imagine what I mean by observing, it could be as simple as a collision with another molecule. Chemistry, we think about collisions and reactions. The collision counts as an observation of a system. So when that collider comes in, it's going to, the molecule that's reacting, this molecule is going to be at some length, bond length. And 16% of the time, the length is larger than what you would expect classically for a bond of that energy. So you can kind of think that the potential at this energy is 16% leak. Right? The energy, the bond leaks out probabilistically out of the potential. That has some deep consequences in chemistry. That you have these leaky bonds. Atoms can be in places in a bond that you don't expect them to be. Let me show you an interesting example of where this becomes important in chemistry. Imagine we have a reaction where we go A and B, you have a diatomic that collides with C to form A plus C and B, a substitution reaction. Okay. I want to think about this reaction. And I'm going to draw a coordinate, a reaction coordinate for this mechanism. Got a barrier, and it's exothermic. Right, so this down here is A and C. This is A and B. And then we have a transition state that looks like B, A, C, right there. Okay. Simple substitution reaction. So thermic over there. All right. Well, let's think about the molecule AB. AB has some vibrational states, some vibrational energy. So we could put energy levels for AB, the vibrational energy levels in this potential, this energy potential. So we could just mark them, right? So let's just say, for instance, that for the AB rotation, this is V equals 0. And then we've got one at V equals 1. And we'll say that V equals 2, for instance, just happens to be right at the barrier. I'm going to move those labels so they're going to be in my way. Just a second. I'll put them on the left. So you can imagine this is an exaggerated plot. There's probably many, many, many more levels than just 3, but just bear with me. Let's think about what the wave function of AB looks like in those regions. Okay, so the V equals 0 wave function has some peak here. And it kind of tapers off like that into the potential. Of course, the probability, right? The probability that the particle is in this potential is pretty small. And if a particle is found here, it can't really do anything, right? Because it's stuck in the barrier. There's no escape. Right? So there's no escape. So there's no leakiness. Because there's nowhere for it to leak out. In order for it to leak out, there has to be some probability that it ends up on the other side of the barrier, A and C. Right? What is going to happen here is that if AB vibrates and it reaches, the bond reaches kind of into the barrier region, it actually just reflects back like a wave. It hits a wall and it reflects back. So if you watch the bond vibrate in this level, you would see it vibrate and oscillate and bounce back and forth in this potential, and it would reflect off of the wall. So it would never really transmit like through a leaky potential. This potential is harmonic, kind of looks like a particle in a box, and it's trapped in there. But once I get to V equals 2, right, you can see that the potential now doesn't really look quadratic anymore. In fact, it tapers off. So the potential, the wave function for this part, well, it'll oscillate. Right? But there's some probability that it can go over the potential like this, and then it's going to taper off like that. Actually, let me do this as psi squared, so it's going to be all positive. Okay. Now, if I put my system at this excited state, right, there's some probability, right, that this system is through the barrier. Right? It's got some probability in that tail that extends over the barrier. And so what will happen is that every once in a while, this molecule that's at V equals 2, this excited molecule, is going to end up, you're going to see it on the other side. Occasionally, it's going to have some probability that it's more represented by the potential on the right. So you can continue this on, right? And so every once in a while, you're going to find a molecule over there, right? And this system, and it's eventually going to collide and cool down to some level here. And then maybe if this V equals 1 state is close enough to the barrier, there might even be some potential for things to leak out of here too. So if the idea here is that if the reactants are close enough in energy to the thin part of a potential, separating it from products, then there is a non-zero probability products will form, even when reactants don't have sufficient energy to react. Right? Because the vibrational potential is leaky, if your potential is narrow enough, this reaction potential is narrow enough, the bond may leak out through that barrier and end up on the other side. Right? We have a term for this, and I'll give you some examples of how this works. Some examples in chemistry how this works. This is a I don't want to call it a technique, it's a phenomenon. This is called tunneling. Right? And certain types of atoms, certain types of reactions are tunneling reactions. And what tunneling reactions are reactions that occur and complete. They go through a reaction, but they're in a state that doesn't have enough energy to get over the barrier. So if you were to look at the thermodynamics of the reaction, you'd say the rate is basically negligible, right? The barrier is so high that there's no chance of reacting. But due to the fact that the bond may be kind of floppy and leaky, there's some probability that the reactants may leak through the barrier and end up on the other side because of the sleepiness. And that process is called tunneling. There's lots of really interesting lots of different cases that this will happen. Here's a great example from chemistry, from organic chemistry. The 1,3 hydrogen shift. All right, let me show you what this looks like. So you have what's called this is called the allocation. And there's a hydrogen here. Okay, this has a resonance structure. 'Cause where the H moves to the other side. So this has a barrier. The activation energy is not equal to 0. It has a barrier. Okay. And you go measure the relative rate where you have the H atom there, and you go measure the rate, and you find that the rate is 1. It's just a relative number, 1 to 1.0. And then you replace that hydrogen with a deuterium, right? A heavy atom, right? It's an extra neutron, twice as heavy. And you find that this reaction is 100 times slower. It's actually probably closer to 0.1. 10 times slower with deuterium. All right, what's the difference between hydrogen and deuterium? Hydrogen has no neutrons, deuterium has 1 neutron. So the only difference between these two atoms is that this is 1 AMU and this is 2 AMU. Why is it that, okay, and remember the Bohr-Oppenheimer approximation. Remember I said that the nuclear properties are independent from the electronic ones. So deuterium reacts exactly the same way hydrogen does. They're the same electronic species. They just have a neutron difference. But here the kinetics are dramatically different. Why is that? What is changing? If you think about this system as due to vibrations, you have some vibration of the CH, right? This H has to kind of is probably vibrating like this, right? The primary vibration for that hydrogen is a stretch. And so the motion of this hydrogen as it moves around maybe has to do with this stretching motion. It doesn't really matter, some motion, right? And some vibrational motion facilitates it to go from one side to the other. Okay? And you ask the question, well, what's the vibrational frequency of that? Well, okay, it's got some force constant. I don't really care what it is. Right, so you can think that we have a frequency for H, which is equal to K over mu for this molecule, where the hydrogen atom is there. And then we have the frequency of vibration for the deuterated species, which is the same K. It has the same K as the hydrogen because the deuterium doesn't affect the bond at all. The force constants of structure is a function of the bond strength, how strong the bond is. Deuterium doesn't affect that at all.
The K being the rate.
K being the rate. The big one? The big one or the big one's the force constant, the stiffness of the spring.
Oh, okay.
This is the spring constant.
Okay.
And so the deuterated species and the hydrogen species have the same K. But deuterium's mass is heavier, right? You've doubled the mass of the thing that's vibrating. So what does that say about the vibrational frequencies? Well, by definition, this has to be greater than that because mu H is smaller than mu D. So the denominator is bigger here, so this is smaller. So if I go look at my energy levels in this potential here, those are my hydrogen ones. Where would my deuterium ones be? They'd be slightly lower. The frequency has dropped. So my deuterium vibrational levels for the deuterated molecule would be these purple levels right here. They'd be slightly smaller. Right, so what happens is all the vibrational levels for the molecule go to lower energy of deuterium. So that means every level is slightly further away from the top of the barrier, all things being equal, all other things being equal. So the energy gap between a given vibrational level and the barrier is larger for deuterium than it is for hydrogen. And therefore the rate drops because the closer you are to the barrier, the faster the rate is. So what we're seeing is a difference and something to do with the vibrational frequency of the molecule slowing the reaction down. And the only thing that can describe that is that you're making the potential less leaky by making the bond heavier and lowering its frequency and its energy. All right. So in general, if a hydrogen is tunneling, so just in general, if hydrogens are tunneling, meaning that they're using their leaky potential to escape a barrier, through a barrier, they're tunneling through the barrier, the deuterium will tunnel 10 times, 100 times more slowly. So this indication here of a 10x rate difference is a hard tell for tunneling. And this has a name for it. This whole expression is called the kinetic isotope effect. Now, you may ask the question, if it's not tunneling, what would the rate difference be? Right? So I'm saying if it's tunneling, it could be 10x, 100x. I've even measured a kinetic isotope effect of 1,000x. The deuterium reacts 1,000 times more slowly than the hydrogen. What would the interesting question you may ask is, what is the ratio difference for a reaction that involves hydrogen, but doesn't tunnel, just a normal reaction? Goes over the barrier, or Arrhenius equation, just normal old Gen Chem or go. That ratio is about 10%. By switching to a deuterium on a reaction that uses a hydrogen, the rate changes by only about 10% on average, give or take. But if it's tunneling, it changes by orders of magnitude. All right. So what you can do to figure out if a mechanism is tunneling or a classical mechanism where things are going over the barrier like billiard balls is to measure the rate with hydrogen and deuterium. And if you have a huge difference between them, then you know the reaction is tunneling. The rate difference is about 10% or something like that. You know it's a traditional reaction. All right, so this is a really classic example of a tunneling reaction. And this hydrogen is bouncing back and forth rapidly on the order of 10 picoseconds or something like that. It's really, really fast. The system is constantly sampling each other. So this hydrogen is literally just bouncing back and forth like a vibrator. Not a vibrator, I'm sorry. Like something vibrating, like an oscillator, bouncing back and forth at a very rapid rate. Right? Even at room temperature, even at cold temperatures, right? It still does that because the hydrogen bounces through the barrier. It leaks, the leaky barrier. Okay. All right. So there are, you might ask, well, what things tunnel? Generally, because it has to do with things that when you substitute them with something heavier, they have a large mass change. So hydrogen and deuterium is a really good example. Hydrogen is a very, very leaky atom. It loves to tunnel through things. Electrons in particular are really, really bad at tunneling, are really, really good at tunneling. So small, light things, it turns out, things that are light and things that are small, that tend to have large vibrational displacements, they tend to tunnel fairly effectively. But it's very rare to find, say, like a carbon atom or a methyl group, something large. Very, very rare that they tunnel. They're just too heavy. Hydrogen in particular is really good about it. There's even one of the things that keeps people from getting down to a specific pressure. Imagine you want to create a perfect vacuum in your lab. The best vacuums in the world are about a quadrillionth of an atmosphere. Yeah, a quadrillionth of an atmosphere is about the best you can get. And you can't really go any lower in pressure than that. That's still about 2 orders of magnitude higher than interstellar space. 2 or 3 or 4 orders of magnitude higher. We could never get down to interstellar space pressures in labs because tunneling actually bottlenecks us. When you have a stainless steel chamber, stainless steel or aluminum, it's got some thickness. And as you pump it down, remember in metal has spaces between the atoms. There's gaps in the metal. There's defects and things like that. It's randomly distributed, and of course, there's space in between the atoms as well. You can kind of think of that as like a barrier, right? There's a barrier, an energetic barrier for things to diffuse from outside the chamber and inside the chamber. And what turns out is that barrier becomes easier and easier to tunnel through with or to leak through the greater the pressure differential. So when you have a really, really low pressure in your chamber and really high pressure in the atmosphere, in the environment, it's really easy to get things to leak through. And the thing that bottlenecks you at the highest pressures that you can achieve is the tunneling of hydrogen through stainless steel. So there's a quantum mechanical limit to pressure, to how low we can get back, because you're eventually can't get away from the fact that the hydrogen literally teleports from one side of the stainless steel to the other. Right? So what are you supposed to do? Right? It's impossible. So that limits us to getting pressures that low because the hydrogen gas in our atmosphere actually diffuses and tunnels through the metal. And so you never get pressure down because you just have magically atoms starting to appear in your chamber that shouldn't be there. And hydrogen is very commonly does this. So this keeps us to about 10 to the minus 13 torr. It's about 10 to the minus 15 atmospheres. That's about as good as we can do. After that, hydrogen starts to dominate the leak rate. Okay. So I've got another little bit of time. Let me pull up my next set of notes. Wrong notes. Oh yeah, that's right. My notes from yesterday. So my screen failed. I did all my notes yesterday on the board. So I don't actually have my notes. So let me just pull up some old notes and then maybe I'll keep moving. Okay, this is a couple lectures from now. Okay. All right. So what I want to start talking about now, get us going, is to think about the most common application of vibrations, which is vibrational and infrared spectroscopy. Right. So you guys learned infrared spectroscopy at Borgo. You learned about how to recognize functional groups based on their stretching frequencies and their bend frequencies. And you can classify different types of CH stretches, sp3, sp2, carbonyls at 1700 wave numbers. Let's talk about those spectra. All right, we'll start thinking about that. That's really a nice way to think about vibrations, is again to probe vibrations experimentally, which is with light. And we can start thinking about vibrational spectroscopy instead of just vibrations. So before I do that, I want to get us all on a language, on the same page linguistically about vibrations. Because this has us now introduce, it turns out that we're kind of in, I don't know how to say this, an awkward energy scale for vibrations. We're not really, I'll just put it this way, it's not really appropriate for us to use joules for this. It's not really appropriate for us to use kilojoules per mole for this. Right? We should think of an appropriate energy unit for vibrations that's relevant for chemistry. And so I just want to talk a little bit about units for just a minute. If I can find this nice discussion about this. Where is it? It must be the next page of notes. Yes, here it is. So I want to just talk about energy today, just units of energy, because we're going to start thinking about spectroscopy. Basically, every time we come up with a new analysis of some problem in chemistry, we're going to want to start talking about the energies, and therefore we're going to start wanting to talk about spectroscopy. because that's the way that we probe these things. It's through light. So I want to make sure that we all have a language that we can share. And I want to talk a little bit about those units. All right. So we have a primary organizing principle that allows us to calculate energies in our system in quantum mechanics. Just one equation. That the energy of a system is equal to h bar times its frequency, right? Planck's law. Of course, this is the frequency, which is in per seconds. And remember, this is different than omega. This is also, I could write this as well. This is equal to h bar omega. And this is what's called the radial frequency, which is radians per second. And frequency is 2 pi radians per second. Okay. And so nu is the frequency of going around an entire circle, and omega is the speed at which we go 1 radian, 2 pi radians per circle. Okay. So that's our organizing principle, that energy is related to frequency of a wave through h bar. Right. And our baseline unit for energy, of course, is joules. For energy. Okay. But what this is telling me is that if I have energy, frequency is also an energy. They're proportional by h, right? So I have an equivalent frequency unit of energy. Right, which is nu, which is equal to E over H. Okay, so that gives me an energy unit, right? So seconds one, which is also called hertz. This is an energy unit for light. And we can also write just equivalently that omega is equal to E over H bar. Right? And of course, this tells us that E is, I'm sorry, no, that's not, is omega over 2 pi. Right? That's our relationship between the two. All right, so let's just do a quick calculation. All right. So what is 1 joule in frequency? Okay. So what's the frequency of that? Well, we can calculate 1 joule over H, which is 6.626 times 10 to the 23 joule times seconds. You can see the joules cancel out, and we get per second. And as you can see, this is a really large number. We're taking 1 over minus 23. Sorry, that's the wrong number. I got Avogadro's number stuck in my head. My apologies. 10 to the minus 34 joule seconds. Right? That's a big goddamn number. Right? 1 over 10 to the minus 34. Right? This is equal to 1.5 roughly times 10 to the 33 per second. I don't even know. I couldn't even tell you what the metric prefix for 10 to the 33 is. I could tell you what 15 is and 18 is, but beyond that, I have no idea. That's a huge number. In fact, this is roughly the amount of energy that 2 protons collide at in the LHC. Right? The most powerful collisions in the entire world between 2 particles barely puts out 1 joule of energy per collision. Now imagine 2 tiny protons hitting each other so hard that they put out 1 joule of energy. 1 joule of energy is about the energy of a baseball thrown by a professional pitcher. Imagine having 2 protons smack each other an equivalent amount of energy as their role is chapped in baseball. Right? It's a head crusher. Right? It's a lot of energy. Okay, so what that means is that the energy units of quantum mechanics are very, very small. Right? 1 joule is an insane frequency. There is nothing, there is no light source on Earth with a frequency that high. In fact, I'm not even sure there are extraterrestrial light sources with energies that high. Yeah, there might be. Maybe some really high energy gamma rays from black hole collisions and stuff, maybe supernova might get you there, but very close, very far. But I don't think that close. So that's a huge number. Okay, but there are other ways to talk about energy besides frequency, right? This is not right. If we have some process that's in the joules, then we should never talk about hertz, right? Because 1 joule is just an insane number. Who the hell even knows what 10 to the 33 looks like? So we have other, we need to choose other types of units that are more appropriate for communication. Right, 1 joule is a really nice number. What are some units in spectroscopy that look like 1 joule, right? Things that are on the order of about a unit. Obviously, per second is not going to be very useful, at least in this context. But we have another option. We can think about the wavelength of light, which is lambda is equal to c over v, the frequency. Okay, so we can plug that into Planck's law and say that E is equal to hc over lambda. Okay. So we can also then say that the change in energy between 2 states is equal to hc between, let's say, 1 and 2. 1 over lambda 2. 1 over lambda 1. Okay. So this is an inverse scale for energy. So as wavelength gets longer, energy goes down and vice versa. So let's do an example. One of my favorite wavelengths is 532 nanometers. Seems oddly specific. Does anyone happen to know what's at 532? You know what color? You're a little far from yellow, but you're close. Yeah, green. This is a green laser pointer. Like a classic green laser pointer. All right, let's calculate how much energy is in a green laser pointer. Right? You're shooting a beam of photons. You can think about a mole of photons out of a laser pointer. Laser pointer distributes a lot of photons. We can calculate how many it distributes. That might be a fun calculation in the future, but it's a lot. All right, a mole of photons is not very many. So let's see if we can calculate how much energy that contains. So the energy is going to be equal to hc over lambda, which is 6.636 times 10 to the minus 34 joule seconds. The speed of light is 299,792,458 meters per second. And our wavelength, we need to put in meters because we're in units of meters up here. 532 times 10 to the minus 9 meters. Okay. So we can calculate that. That's going to give us an energy in joules, right? The seconds cancel out, the meters cancel out. We're just left with joule. And this is equal to 3.74 times 10 to the minus 19 joules. All right, well, that's not very much energy, right? So, but that's how much energy 1 photon at 532 puts out. Right? This is the energy of 1 photon. Let's ask, because I don't feel like doing a calculation right now. Let's just ask Gemini. what is the average number of photons emitted per second by a 5 milliwatt green laser pointer? All right, 5 milliwatts is a typical class 3 laser pointer you would buy on Amazon. It's about 10 to the 16 per second. All right, so it's actually a little less than a mole. A lot less than a mole. It's about 10 to 16, that's 10 to minus 7. It's about a micromole, right? About 100 nanomoles, 10 nanomoles of photons a second. All right, so let's just look at the molar. Well, wait, let's just go ahead and do the math. Why not, right? So we'll just say that on average, there are, what did I say there was? 10 to the 16? Yeah, 10 to the 16. 10 to the 16 photons a second, right? Which means that, let's just go ahead and do it really quickly. 1E16 divided by 6.02 E23. All right, we'll calculate the number of moles. That's 16 nanomoles of photons per second. All right, so we can calculate the energy dose.
Wait,
per second.
The what? What
10 to the 16.
Okay.
10 to 16. So that's 16 nanomoles of photons per second. Oh, sorry. Yeah, 16 nanomoles per second. Right, and so the total amount of energy per second, right? So energy delivered over time. This is equal to the power is equal to 3.74. Oh, sorry, let me calculate this a little more. Right, so that's going to be 3.74 times 10 to the minus 19 joules times 10 to the 16 photons times 1 over Avogadro's number. Right. Wait, did I have that right? Oh, sorry. Hold on a second. Let me get this math right. Oh, okay. No, hold on. Let me, I know what I'm doing wrong. So let's do it in moles first. So we'll multiply this by Avogadro's number, right, which is going to be 225 kilojoules per mole. Okay, so that means that the power delivered by a laser pointer is 225 kilowatts per mole. And then therefore, for a laser pointer, we can multiply that by nanomoles, 10 to 16 nanomoles. So that's going to be, you just go ahead and, so that's going to be 2.25 E3. That's 225 kilowatts. That's 225 times 10 to the 3. And then we're going to multiply it by the number of moles we have, which is times 16 E minus 9. All right, so we have 0.0036 kilowatts per second, which is equal to 3.6 watts. Did I get that right? Yeah, 3.6 watts. That's a lot of power. All right, so a laser pointer, you take all of the photons in the laser pointer and put them in a line. Put them in a line, right? So it's an infinitely thin laser. Put them all in a line and have them blast a single point. In 1 second, you deliver 3 times more power than 100 fastball thrown by Nolan Ryan, the fastest pitcher in MLB. Tons of energy. Right? That's why laser pointers can heat things up and blow things up if you have enough juice. Things will just blow things apart. So that's a nice conversion factor. This is why we use lasers to do chemistry. Laser pointer can put in macroscopic amounts of power into a system. The question you might want to be asked is if a mole of laser, like of green laser, gives us 225 kilojoules per mole worth of energy to work with, how hot would you have to get a heater to deliver the same amount of energy? Right? So we can convert that 225 kilojoules per mole into a temperature using the gas constant, using R. And this is an equivalent temperature of 27,000 Kelvin, hotter than the surface of the sun. This is the power of light to deliver energy. It can deliver energy in a chemical way more efficiently than heat does by orders and orders of magnitude, because I can go to Amazon and buy a 532 nanometer laser just fine that will blow up just about anything I throw in front of it. And if good luck trying to find a heater that gets you 27,000 Kelvin, much less 10th of that. 2,700 Kelvin is already hard enough. This is why we don't really use heat to blow molecules apart. You can, it's just not very efficient. Lasers do a much better job of it. Right. One more unit. We're doing vibrations. So we need to think of an appropriate unit for vibrations. And you guys probably remember from Orgo that the x-axis in your vibrational, your infrared spectrum, were in wave numbers, inverse centimeters. So let's see where that unit comes into play here. All right, the final unit I want to talk about for spectroscopy is the wave number. Okay. I usually use labels, two different labels. Either I use omega, squiggly, or nu, squiggly. Anytime you see a squiggly, this means wave numbers. Right? What are wave numbers? All right, the definition of a wave number is equal to 1 over its wavelength. Right, so it has units. Traditionally, we usually report them as inverse centimeters. Okay, so how would you convert wave numbers to energy? Well, remember that E is equal to hc over lambda, so we can directly substitute in omega, which is hc omega. Okay. So the most common unit. Which time do I? Okay, good. I'm almost done. Of course, is inverse centimeters. That's pretty much the only unit we use in chemistry. I don't know anyone who uses other length units besides centimeters. All right, and so let's just look at some conversions really quickly. So let's imagine omega is 1 inverse centimeter. Okay, that means that the wavelength is 1 centimeter. That's an easy conversion. And remember that frequency is equal to c over lambda, which is roughly 3 times 10 to the 8 meters per second, divided by 1 times 10 to the minus 2 meters. It's a centimeter. And this means that the frequency of equivalent frequency turns out to be exactly 29,979,458 gigahertz. So what we often say, right, what we can do is make a conversion here. You can do a conversion chart here. So that one wave number is equal to roughly 30 gigahertz of frequency. By the way, if you're curious, this is the microwave. You guys know Starlink, that wireless internet service that Elon Musk sells? Starlink, that runs at 24 to 40 gigahertz. So one wave number is about the frequency of Starlink. This is equal to 11.96 joules per mole, or 1.44 Kelvin, or of course, 1 centimeter wavelength. Okay. So we've got a bunch of different units that we can use, right? We can use a wave number, we can use frequency, we can use energy, we can wavelength, we can even use temperature. Astronomers use temperature for energy, which is really stupid. It's really annoying. Their energies are crazy. But they'll report things in Kelvin as an energy. So they're all interconverted. All right, so let's just go look really quickly. Right, at a regular IR spectrum, I'll just Google it. Right, you guys have seen these a million times, right? Something that looks like this. This one's for aniline. So aniline or penicillin? Vanillin. This is vanillin. Oh, that was a terrible picture. Here we go. Right, you've seen things like this. Right, and the wave numbers in a typical spectrum, IR spectrum, range from 500 to 4,000 wave numbers. Okay. So this is the infrared. Right, infrared tends to be on the order of 1,000 to about 6,000 wave numbers. So that's usually what we call infrared. And so, of course, what is the wavelength for that? 1,000 wave numbers is 1 over 1,000 centimeters of wavelength, which is 1 micron. Right? So the wavelength of light at 1,000 wave numbers is 1 micron. At 2,000 wave numbers, it would be half a micron, which is 500, and so on and so forth. Sorry, it's 10 microns, 10 microns, excuse me, 10 microns. It's 10 microns, and then 2,000 would be 5 microns. This is 2.5 microns, right, which is 2,500 nanometers. Okay, so this is longer wavelength than visible. Visible ends at around 800 nanometers. These are all much longer wavelengths by about an order of magnitude from visible light. And so what we can say is a typical IR experiment. So typical vibration has a frequency, h bar omega, let's just say of roughly 2,000 wave numbers. So what's the wavelength of that? It's 1 over 2,000 wave numbers, which is 5 times 10 to the minus 4 centimeters, which is equal to 5 microns. Right, and we can convert to the other ones as we please. Okay. So we're going to use, whenever I talk, and actually in the vast majority of this class, I will talk in units of wave numbers. Wave numbers are really, really convenient for quantum mechanics, especially in chemistry, because a lot of really interesting things in wave number regions. So we're going to use that. We're going to use wave numbers a lot going forward. I just want to make sure everyone's on the same page about wave numbers. Right? It's a unit of energy. Unit of energy. Just happens to have inverse units of length, which seems odd, but remember that energy, wavelength, and frequency are all interconvertible with Planck's constant and the speed of light. If you have those two constants, they're all the same thing. Okay, so what we're going to do on Monday is to take this language and start looking at vibrational spectra. One of the things that I want to consider, just for us to, and I'll walk away from this in 20 seconds, is that in a harmonic oscillator, all the energy levels are equally spaced. So if you wanted to go do spectroscopy on this, and you want to excite the system by one level, you go 0 to 1, 1 to 2, 2 to 3, and so on. They're all right, because that's what we do in spectroscopy, right? We tune our light to be at some energy difference between two levels. We get an absorption. So we would tune our laser at h bar omega, we would expect to see an absorption in our spectrum. But here's the problem. What level are we? Every single transition has H bar omega. So the 0 to 1 transition, the 1 to 2, the 2 to 3, the 3 to 4, they're all at the same frequency. So how do I know which one it is? Right? So that's one of the complications of the harmonic oscillator, is that it's so simple that everything overlaps each other. What we would predict here is that there's only one line for the change by one transition. Only one line. They're all overlapping. So we're going to have to figure that out and resolve that. What we're going to find out in an experiment, that's not true. If we don't see just one overlapping line, we see many. So we're going to have to figure out what we're doing wrong here. And we'll have a really nice discussion of that on Monday. All right. Have a good one, guys. Problem set will be out over the weekends.